Okay, so now that we've talked about the basics of hypothesis testing, now we're going to actually apply the concept to doing a hypothesis test on a claim on a population proportion. The next section will be on a population mean, and then the last would be on a population standard deviation. Now, as mentioned before, a hypothesis test is going to be a very systematic approach. Okay, in fact, we're going to use the same 6 steps throughout all hypothesis test problems, and we're going to go over those shortly. Okay, but before that, we have an example to motivate this process. A basketball player says he makes 70% of his free throws. We believe he makes less than 70%. Okay. Now, to test our claim, we have him attempt 50 free throws. He makes 29 of them. Okay. His sample proportion of made shots is, well, 29 out of 50, right? That would be your sample proportion, because he says that he makes 70% of his free throws. But on this occasion, he made 58% of his free throws, right? Approximately. So what can we conclude about our claim based on the sample data? Okay, when we go through the outline of the steps, our first step was always going to be just stating the hypothesis statement, which in this case, we are talking about a proportion. And how do we know? Well, because they say proportion straight up in the problem. Other ways that you know that you're talking about a proportion are words like percentage, or even the word rate kind of comes up. Those are the 3 main indicators that we're talking about a proportion. Okay, so if we're talking about proportion, there's a claim on a proportion. So the null hypothesis always has the equality, and the alternative here has either a less than, greater than, or a not equal to. Okay, now we're challenging the status quo, right? So we're saying that we believe he makes less than 70%. Okay, so he says he makes 70%, and we believe he's making less than 70%. So the claim is that we are challenging the status quo, which that means it's the alternative hypothesis, and we say it's less than 70%. So less than 0.7. Okay, that is the claim statement. In fact, I'm going to go ahead and highlight that. We believe he makes less than 70% of his shots. Now, the null hypothesis will be that he makes 70% of his shots. Okay, these numbers always match. Okay, these numbers are always going to match. Okay, and then the equality is always going to be on the null hypothesis. If in fact he does actually make 70% of his free throws, right? In this case, he made 58%, but he typically makes 70% of his free throws according to him, right? Okay, so if in fact that's true, what would be the probability that he makes 58% or less, right? So what we're saying is, if that was true, yeah, there's a possibility that it'll be less than 70% on any given day, but what's the probability that he actually made 58% or less? And if we come up with that probability, can we conclude that this is an unusual or a non-unusual event? So if we have a proportion, a sample proportion, p hat, we know this will vary from sample to sample, okay? Or for every 50 throws that he makes, of course, sometimes it'll be 58%. It might be 70% like he claims it should be, but it will vary from every 50 throws, okay? So it has a distribution. And sample proportions under certain conditions are distributed as normal, okay? And the mean of a sample proportion is the true population proportion, which in our case is right there. We're assuming that 70% of his free throws are made, right? Until we have evidence to prove otherwise. So 0.7. And the standard deviation of p hat, as we saw in the section about sampling distributions for a sample proportion, was that it was square root of p times 1 minus p over n. Okay, so in our case, the p was 0.7. 1 minus p is 1 minus 0.7, which we know that to be 0.3, right? And then the n is our sample size. So how many free throws did this person take? 50. All right, so this is the mean, and this is the standard deviation. And the question is, how do we find the probability that he makes 58% or less? Okay, so we need to draw a bell-shaped curve because we know this is a normal distribution. We are assuming that he does make 70% of his shots, right? So that should be the average, right? That's where the center is, right? But sometimes he makes probably even more than that, somewhere around here, or sometimes he makes less than that. But on average, he makes 70% of his shots. On this particular day, he made 58% of his shots. And we want to see what was the probability that he makes 58% of the shots if he usually makes 70% of the shots. So where's 58? Well, here's 0.70, so 58 should be to the left here. And we want to know the probability that he makes 58% or less. So that area. This area will give us the probability of what we witnessed, which was 58% of his shots being made, or less. So to find the area underneath the normal distribution, we know that to be probability that this p hat is less than 0.58. And for a normal distribution, to find areas underneath that curve, we're just going to refer to our calculator with that function normal CDF. We have our lower bound, our upper, the mean, and the standard deviation. All right, the leftmost value, or the lower bound here, would be negative infinity. In our calculator, that's going to be negative E99. The upper, 0.58. The mean, in this case, it's 0.70. And the standard deviation is that highlighted square root. So square root of 0.7. I would put that multiplication symbol and then 0.3. And then divided by 50. That's how you should put that in your calculator. And we've done examples of how to put this into your calculator in the past. If you calculate this, what you'll get is 0.0320. Okay. So the probability of seeing what we witnessed, which was 58% of his shots being made, or less than that, would be 3%. Okay. We typically consider an unusual event to be less than 5%, unless it's defined in another way. So if the actual parameter value of the proportion is 0.7 was true, then the observed sample proportion, what we witness, of 0.58 or less, would be considered an unusual event. Why? Because it's less than 5%. Since this event is unlikely, then perhaps this gives us convincing evidence to support our claim that the player makes less than 70% of his shots. In other words, this outcome is very unlikely if he usually makes 70% of his shots. So we can conclude that his free throw accuracy is lower than 70%. Okay, so to understand the logic of the hypothesis test. So when observed results are unlikely or unusual, under the assumption that the null hypothesis is true, then we say that the result is statistically significant. When results are found to be statistically significant, then that means we found enough evidence to reject the null hypothesis. Now we're going to talk about the 6-step approach to hypothesis testing. Now there are a few ways to do the hypothesis test. One of them being the classical approach. Okay, that's one with rejection regions and all sorts of stuff. And then the p-value approach, and then a confidence interval approach. Now in our class, we're not going to do the classical method. Okay, that requires like tables and stuff that we're not going to do. We're going to just use technology here. We are going to use the p-value approach. Okay, and in the next section, when we're dealing with two parameters, we will introduce the confidence interval approach alongside the p-value approach. Okay, so the following are the 6 steps. Now for every type of hypothesis test, depending on what we're doing a claim on, in this section we're doing a claim on a population proportion, there's always a pre-screening or certain requirements needed in order to see if we can actually approach it in this way. Okay. You can call it like step 0. For a proportion, that is that we take the sample using simple random sampling. Also, this condition comes up again, that NP times 1 minus P is greater than or equal to 10. There's little 0 subscripts there. I'll explain what that means in just a second. That really just means that the proportion is coming from the null hypothesis. Okay. And then the sample values are independent of each other. Okay, and how do we know if that's true? Well, as long as our samples are less than 5% of the population size, then it's very unlikely to get the same sample again. All right, step 1 is our hypothesis statement. Okay, you can either have a two-tailed test, a left-tailed test, or a right-tailed test. What that typically looks like when we graph it, a two-tailed test will look like this, where you have 2 regions shaded. A left-tailed test would look like this, where you have the left tail shaded, and the right-tailed test will look like this, where you have the right tail shaded. The easy way to remember this is for the less than, it literally points in the direction of the shaded region. For the greater than, it also points in the direction of the shaded region. For not equal to, you know it's going to be two-tailed. Now, how do you know which one we're dealing with? We get that from the claim statement. Okay, so it's always important to highlight the claim statement. We either underline it, or if you have a highlighter, highlight it. Step 2, it's actually the easiest one. In the problem, they'll give you a significance level, okay, which will be an alpha. They might say a level of significance, or alpha equals something. Again, that's the probability of committing a type 1 error. The alpha will be given in the problem. Step 3 is our test statistic. Okay, this is a z-score essentially. Okay, to deconstruct this, this test stat is essentially the difference between what we see in real life and what we assume to be true from the null hypothesis. So this p-hat is the proportion that we get from our data, from our sample data. And this proportion here is the proportion that comes from our null hypothesis. And this here is the standard error, or the standard deviation. Okay, so this is a statistic that essentially gives you the difference between what we expect and what we see. And if the difference is too far off, then we can say the difference may be statistically significant. Step 4, we're going to draw a normal curve, and we're going to label everything. Now, on your calculator, we're going to have to find the area in all these tails, depending on which situation we have. Okay. Now, we could do it like we did in that preview example, where we just use normal CDF, but it turns out your calculator does all that for you in a program called OnePropZTest. Okay, it'll give you that area. And a p-value is just the area of the shaded region. Before we had to use normal CDF for that. But this function in your calculator will do this all for you. We'll do that with an example. And step 5, we're going to have to make a decision whether to reject the null hypothesis or fail to reject the null hypothesis. And that's done by comparing the p-value that we calculate to our significance level. If the p-value is less than alpha, then we reject the null hypothesis. If the p-value is greater than alpha, then we fail to reject. And finally, step 6, we have the wording of the final conclusion. Okay, so this is where we start. If we look at the null hypothesis, in step 1, the claim can either be the null hypothesis or the alternative. And the question is, does the original claim have the condition of equality? The only claim that has the condition of equality is the null hypothesis. So if your claim is a null hypothesis, then we say yes to this. Otherwise, if the claim was the alternative hypothesis, we go in this direction. Okay. Now in step 5, we make a decision. And we either reject the null hypothesis or we don't, right? Step 5. And if we do, then we have one wording for the final conclusion. And if we don't, we have another. So there's 4 different ways, okay? And we'll go through these as we do some problems. And we'll refer back to this page every time we come up with our conclusion statement. And one thing to notice is if your null hypothesis is the claim, then in the wording of the final conclusion, you'll notice that the word rejection shows up. Okay? A very specific claim, one that has an inequality, can be rejected. However, something that is not very specific, something like less than or greater than or not equal to, would be the alternative. And you notice the wording there is support. Okay? So you can either support the alternative hypothesis, or you can reject the null hypothesis, or not reject it, or you fail to support the alternative. All right, so here's our first hypothesis test question. It says, in 1997, 46% of Americans said that they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll, 1,010 adults nationwide, 525 stated that they did not trust the media. At a 5% level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? Okay, so throughout this problem, you have to look out for a few things. And the main thing you want to identify is the claim statement. Okay, and you need to really get good at this. Okay, sometimes it's just followed by the word claim. Okay, other times it's a little subtle. In this particular case, there is a word that says claim, and the claim statement is what? That the percentage of Americans that do not trust the media to report fully and accurately has increased. Okay, so I'm going to highlight that claim statement. And we'll talk about the conditions in just a bit. But let's start with step 1. Okay. Now, once you're doing this in an exam, you're going to have a question like this, which is just a paragraph and then a bunch of blank space. Okay. And on the exam, you have hypothesis questions about a population proportion, a population mean, a population standard deviation. Later on, we'll talk about correlations. So you have to look for keywords to determine what we're talking about. Okay. And we are in the section of proportions. So it's obviously that we're going to talk about proportions here. But the key word that tells us that we're talking about proportion here is the word percentage. Okay, the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997. Okay, so if we're talking about proportion, let's start with our hypothesis statements. That's HO, H1. Okay, and then we have a proportion, because that's the parameter we're talking about. In the null hypothesis, it always has an equal sign. Okay. Now, again, let's read that claim statement. The percentage of Americans that do not trust the media to report fully and accurately has increased since 1997. Okay, well, what was the value in 1997? Well, in 1997, it was 46%. So if it's increased, we are making a claim that it is more than 46%. Right? So we're saying that p hat is more than 0.46. So in this case, this statement is the claim. In other questions, the null hypothesis might be the claim. They might make a very specific claim that the percentage of Americans that do not trust the media is exactly 46%. And that would be a situation where the claim is the null hypothesis. Okay. And then what did I say about this number? Well, this number always matches up with the null hypothesis. These always match up. So that one's easy. Okay. That is a complete step 1. Step 2. Step 2 is the easiest step, and that's just to identify what the significance level was given. Okay. And again, the significance level is just a number, a percentage really, of how often you want to be wrong in your conclusion. Okay, we're only willing to be wrong 5% of the time. So alpha is 0.05. 3. What's your test statistic? Well, for a proportion, the test statistic is your z value. Okay, because it's a normal distribution under certain conditions. Well, actually, before we get to that, let's talk about the conditions here. Did we take a simple random sample? I'm sure they did say something about that. Yeah, if it's a poll, then we assume that these polls are done correctly, so we can just assume that. There's nothing to suggest that it wasn't. And then is this condition met? NP times 1 minus P. All right, what was our sample size? What's our N here? They took 1,010 adults times P. P with the 0, that just tells you that this is coming from the null hypothesis. That's 0.46 times 1 minus 0.46. And what do we get? 250.884, which is clearly greater than 10. So no issues there. Okay, back to the z-score here. The formula here is p hat minus p over the square root of p times 1 minus p over n. Okay. So let's go ahead and catalog what we know, or what we need. Well, we need to know what p hat is. P hat is x over n. That's our sample proportion. Okay. So that means we need to know what x and n are. And again, like I mentioned before, this comes from the null hypothesis. This comes from the sample data. The p comes from the null hypothesis. That is just the 0.46 that we see in step 1. And then down here in the denominator, we have a p, 1 minus p, and an n. Okay, and that's all listed here. All right, so what's our sample size again? That was what, 1,010? So there we go, 1,010. And then we just need to know x. X is those with the characteristic that we're looking for. In this case, those who do not trust the media. So we said that that was 525. Okay. Now, you can actually plug all these values into this formula and you'll get a result. Okay. And that's fine. That's how it's normally done if you didn't have the TI calculator, but we have the TI calculator. So let's go ahead and pull up that function, and that function is called 1prop z test. Okay. Let's go to the calculator. All right, we're at the home screen here. We're going to go to the stat menu, and then we're going to go all the way over to test. Okay, and we're going to look for the test called 1prop z test. Okay, and it looks like it's the 5th one here. Press enter. And what do we see here? Well, it says P, and there's like a little 0 next to it. That's the proportion from the null hypothesis, what we're assuming to be true until we have evidence to suggest otherwise. So in this case, that is 0.46. X in this case is what? 525. N is what? 1,010. And then this part is referring to the alternative hypothesis. They're saying either the proportion is not equal to, less than, or greater than. In our case, what do we have? Well, if you look at the alternative in step 1, it's greater than, right? So we have to go ahead and migrate to that, highlight that by just pressing enter. Okay, now that one's highlighted. And then we go to calculate. Okay, just making sure that you put everything in correctly. All right. So once I press enter, I get this output. Okay. One thing is the very first thing, which is the test stat. That's the z. Okay. If I just round to 2 decimal places, I get 3.81. Okay. Remember, z-scores represented numbers of standard deviations away, right? 3.81 is pretty far away from the center, right? Because that's three standard deviations away. You know, within 3 standard deviations, that should be 99.7% of your data. So 3.81 is pretty far away. Okay. What else do we see here? Well, the next number here is just a p. Now that's not the proportion. That's called the p-value. Okay, this is going to be universal for all these outputs. You're always going to have a p-value here. Now, p-value is the probability of committing a type 1 error. Okay, well, probabilities cannot be more than 1. So why does it say 6 there? As soon as you see that it's larger than 1, in this case 6, you're going to immediately look all the way to the right and notice that it's in scientific notation. You see that e negative 5. So this is 6.858, whatever, times 10 to the negative 5. So it's a very tiny number. Okay. So that tells us how likely it is that we commit a type 1 error if we were to reject the null hypothesis. It's very unlikely. P hat is just the proportion. That's if we were to just divide the 525 by the 1010. And then the n, they just output the 1010 again. Not sure why. No need for that. Okay, so that's a complete step 3. Step 4, make sure you don't clear out your calculator, because I'm going to go back to the calculator to get the p-value from that. So step 4, we're going to draw a picture. We are dealing with the z distribution, so we are dealing with a bell-shaped curve. That's a hint, because later on we're going to deal with things that are not bell-shaped. At the center, it's 0, because we standardized it. Okay. And what kind of tail test is this? Well, if we look at the alternative here, that's saying that it's greater than, so it's going to be a right tail test. So we first have to label the test stat that we just found in step 3. So here's 0. Where's the test at? 3.81. This seems to be way out here. And the fact that we have a right tail test means that we're going to shade to the right. Okay, and what is the area of that shaded region? Well, that is the p-value. And what's the p-value equal to? Well, if we go back to the calculator again, we have 6.859, if I round, times 10 to the negative 5. Now as a decimal, that'll move the decimal place 5 places to the left, which means we're going to have 4 zeros. I just want to show you the equivalent point. Okay. So that p-value represents the probability of committing an error if we were to reject the null hypothesis. Okay. In step 5, we're going to make a decision on whether to reject the null hypothesis or not. So we make a decision. How is a decision being made? Well, if you compare the p-value to the alpha from step 2, our p-value was 6.858 times 10 to the negative 5. The alpha was 0.05. Now, we were willing to be wrong with a 5% chance. In our case, the chance of us being wrong in our decision of rejecting the null hypothesis is much less than 5%. So we're going to go ahead and take that chance because we were willing to be up to 5% wrong. So since this value is less than, we're okay with rejecting the null hypothesis because the likelihood that we are wrong in this decision is very small. So now is the conclusion statement. Remember that flow chart that we had from the previous page? We're going to use that now. All right. So in that flow chart, there was 2 steps that we had to identify. In step 1 was that the null hypothesis has a condition of equality. Basically, is a claim the null hypothesis or is it the alternative? Okay. In our case here, it is the alternative, right? As you can see here. So let's move over to that page here. Okay, so if it's the alternative, we're going to go in the downwards direction, right? So the original claim does not have the equality. Okay, now we're over here. And in step 5, did we reject the null hypothesis? And yes, we did. So to start off our wording for the final conclusion, we say that the sample data support the claim that, and then we restate the original claim. The sample data supports the claim that what? What was that claim? Well, good thing we highlighted it, right? That the percentage of Americans that do not trust the media to report fully and accurately has increased. You can paraphrase that if you want. I think it's fine the way it's read. That the percentage of Americans that don't trust the media has increased since 1997. All right, that's a complete step 6. All right, so let's do a recap here, because we are going to be using these same 6 steps over and over and over. Okay, we come up with our hypothesis statements. Okay, that's the null hypothesis and the alternative. We have to figure out what parameter we're talking about. And to do so, we have to highlight the claim statement. Usually that's followed by the word claim. Sometimes it's a little bit more subtle than that. All right, in this case, we have the proportion, and we said that the proportion of Americans who do not trust the media to report fully and accurately has increased since 1997, and in 1997 that value is 46%. So our claim statement was this here. P is greater than 0.46, and that was a claim statement. And the null hypothesis would be proportion is equal to 46%. And then in step 2, just identify the significance level. It's usually just given to you in the problem. And if it's not, then 5% is a typical value that it's used a lot. And then come up with the test statistic. That's just a formula. You just have to figure out what your inputs are and put those into your calculator correctly, and it'll give you a z-score. In step 4, we're going to draw a picture that corresponds to our test stat. Our test stat, the z-score, which we know is a normal distribution, so it has to be a bell shape. And in this case, this is a standard normal. We have 0 at the center, and we have to label the test stat, which is 3.81, which we found in step 3. And we also have to label the p-value, which also comes from the output in step 3. Okay, and then shade in the correct direction. So there's a lot of things that go on in step 4. And that p-value in this case was less than our alpha. And anytime the p-value is less than alpha, we reject the null hypothesis. If it's greater than alpha, then the probability of making a mistake is too large, right? You don't want it to be more than 5%, so we can't reject the null hypothesis. Okay, so then we come up with our conclusion by following that flow chart, and that's what we have. So let's go ahead and do another one. Example 2, the Mars Candy Company claims that the percentage of brown M&Ms is equal to 13%. A random sample of 100 M&Ms is acquired, and only 8 of them are brown. Use 5% significance level to test the claim. Okay, so in this case, we need to identify the claim statement. What was a claim statement? Well, it's usually in the first or in the last sentence. Sometimes it's elsewhere, but usually it's in the first or the last sentence. So in our case, it's the first sentence. The Mars Company claims that the percentage of brown M&Ms is equal to 13%. Okay, the percentage of brown M&Ms is equal to 13%. And what type of parameter are we talking about? Well, it's a proportion because that word percentage shows up. Okay, so let's start with step 1, null hypothesis alternative. So we're talking about proportion here. The null hypothesis always has an equal sign. And in this case, let's refer to that claim statement, the highlighted sentence there. What are they suggesting? Well, that it's equal to 13%. Well, they're saying that proportion is 0.13. In this case, the null hypothesis is the claim statement. I always like to label that. Labeling that as the claim statement early on in the problem will definitely help us in step 6 when coming up with our conclusion statement. So keep that in mind. Always label your claim statement. And then what would be the alternative? Well, the opposite of equals is not equals. Okay. And again, this number also matches. So that is a complete step 1. Step 2, that's just identifying our alpha here, our significance level. They said it's 0.05. Again, that's the willingness of being wrong in our decision. We're willing to be 5% wrong. Now at this point that we know the P, if we can figure out what the N is, we can figure out if the conditions are met. Is this a simple random sample? Well, yeah, they said it's a random sample there. NP times 1 minus P, is that greater than 10? And also, is our sample smaller than the population? Yeah, 100 M&Ms is what we have. That's our N, and that's definitely less than 5% of all M&Ms, right? So let's figure out what the NP times 1 minus P is. N being 100, P being, coming from the null hypothesis, 0.13 times 1 minus P. Okay, so this is equal to 11.31, which is just barely over 10. Step 3 is our test stat. In this case, we're dealing with the proportion again, so we're going to have our z equals p hat minus proportion over the square root of p times 1 minus p over n. Okay, so the p hat is just composed of x's and n's, right? And the proportion from the null hypothesis is that value. Again, this comes from the null hypothesis, and this comes from our sample data. Okay, our sample data, well, our sample size was 100, right? There's 100 M&Ms that we took. And of those 100 M&Ms, how many were brown? That's what we're interested in. Well, we said that there's 8 of them that were brown. And the proportion from the null hypothesis was that it was 13%. Okay, let's go ahead and run this through one prop z test. Again, if we go to stat and then test, one prop z test, the proportion from the null hypothesis was 13%, so 0.13. X was 8, and it was 100. And in this case, what was our alternative here? If you look at the alternative in step 1, it was that P was not equal to 0.13. So we just have to make sure that the not equal to is highlighted. So by pressing enter over it. And then let's go ahead and calculate. All right, so we have a test score that is negative 1.48, and that's fine because our sample proportion was 8%. The population proportion was 13%. So when we subtract those numbers, we do get something that's negative. Okay, now the p-value comes out to be 13%. Okay, so that's larger than our alpha. Okay, so we'll talk about that in step 4. All right, so that's a complete step 3. In step 4, we have, again, we're dealing with a bell shape because we're dealing with the proportion that's normally distributed. 0 it is at the center because we're dealing with the z-score. Now our test stat from step 3 was negative 1.49. So it's over here, negative 1.49. And what kind of tail test do we have? Well, since the alternative is that it's 2 tails, we need to shade both to the left and to the right. Well, on this case, we're going to shade to the left. Now we also need its positive counterpart for this, okay? So this just makes it just a slightly harder test to pass. That's what that does. Now the p-value that we get in our calculator was what? It was 0.1371. And then that area essentially is the sum of both of these tails here. Okay. All right, so that's a complete step 4. Okay, so now in step 5, we have to compare that p-value. We make our decision. How is the decision being made? Well, it's being made by comparing the p-value to your significance level in step 2. P-value being 0.1371, significance level being 0.05. And the p-value is actually greater than. Okay, again, the p-value represents the probability of being wrong if we do decide to reject the null hypothesis. Okay, if we reject the null hypothesis, there's a 13.71% chance that we're wrong. Okay, we're not willing to take that risk because we were only willing to take up to a 5% risk. Okay, that was the cutoff. So we're not going to reject the null hypothesis. So we fail to reject the null hypothesis here. Because if we do, there's a pretty high chance that we're wrong in that decision. Step 6, we make a conclusion statement. Okay, now in this case, if we follow that flow chart, the claim statement was a null hypothesis, and we failed to reject the null hypothesis in step 5. So let's go up there. All right, in this case, the claim statement was a null hypothesis. All right, so we're going to go this way, and we failed to reject it, so we're going to go that way. You see that? So we start our conclusion statement with, there is not sufficient evidence to warrant rejection of the claim that, and then we state the original claim, which hopefully we highlighted. Which we did right there. The percentage of brown M&Ms is equal to 13%. All right, so we say there is not sufficient evidence to warrant rejection of the claim that, and then we talk about the claim statement here. The percentage of brown M&Ms is equal to 13%. That the percentage of brown M&Ms is equal to 13%. So the fact that we, from 100 M&Ms, only 8% were brown, even though that's lower than the 13%, that wasn't significantly lower than the 13%. Mostly because the sample size wasn't large enough. If this was 8% out of 1 million M&Ms, then we would definitely get something that's more significant. Example 3. A poll of 1,068 adult Americans reveals that 48% of the voters surveyed preferred the Democratic candidate for the presidency. At a 5% level of significance, test the claim that less than half of all voters prefer the Democrat. Okay, so let's go ahead and highlight the claim statement. Okay, test the claim that less than half of all voters prefer the Democrat. Okay, that seems to be the claim statement because it's usually followed by the word claim. Again, sometimes the word claim doesn't even show up in the problem, so it's a little bit more subtle. But this one was pretty straightforward. Okay, less than half of all voters. So half is really the key word there, right? Half pertains to a percentage, right? Or proportion. So let's start with step 1 here. We're talking about the null hypothesis and the alternative. Those are our hypothesis statements. What kind of parameter are we talking about? Again, in this case, the word half is the only thing that indicates that we're talking about proportion here. So they didn't even say the word percentage or proportion or rate or anything like that. The null hypothesis always has equality. Okay, now in this case, what are they saying? That less than half of all the voters prefer the Democrat. So they're saying less than half. What does half mean? Well, that's 0.5, right? And again, these two numbers have to match. And then the alternative was the claim statement in this case, right? That matches up with the highlighted sentence. That is a complete step 1. Step 2, let's identify our significance level. They told us that that is at 0.05. Now at this point, again, we can meet the conditions now that we know what the proportion is from the null hypothesis, which is 0.5. Do we know the sample size? They took a poll, right, of 1,068. So our sample size is going to be 1,068. And of course, 1,068, is that less than 5% of the entire population? Yeah, that's less than 5% of everybody in the country. So that's met too. So let's go ahead and do that. NP times 1 minus P. Let's see if that's greater than 10. Most likely it is. As long as that N is pretty large, then we most likely will get this. 1068 times 0.5 times 1 minus 0.5, which is 267, which is definitely greater than 10. Okay, so the conditions were met. So this definitely follows a normal distribution. All right, so step 3, we're going to come up with our test stat. Our test stat is that Z equals P hat minus P. Again, we're taking the difference between what we see from our data and what we suppose is true from the null hypothesis. Okay. Again, our inputs here are the P for the null hypothesis, x and n. That's how it's listed in our calculator. Okay, so from our calculator we have one prop z-test. So the proportion from the null hypothesis is 0.5. Again, this value comes from the null hypothesis, and this value comes from our sample data. P hat is x over n, right? So our sample data is that n, which was, what, 1,068 people surveyed. And of those, we had what? Oh, we had that 48% were. Okay, so this one's a little bit different. Our calculator only takes on x's and n's. Okay, what they actually gave us was what? They actually gave us what p hat was. Okay, so I'm glad this problem came up, because we're going to have to back into what x is. Okay, so we know that p hat is equal to x over n. All right, we need to solve for x. Well, if we solve that for x, x is equal to p hat times n, correct? They told us what p hat was, that's 0.48. They told us what n was, which is 1,068. So we can figure out what x is. We get 512.64. Now your calculator doesn't allow for decimal values for x because they're expecting a whole number. So let's just round to the nearest whole number. In this case, 513. All right, let's go over to the calculator. If we go to stat and then we go to test, we go to one prop z-test, which is that one. The proportion from the null hypothesis was that it was 0.5, right? The x here is, what, 513? The n here was 1,068. Again, you don't want to get those x's and n's backwards because it'll give you an error. And then the proportion from the alternative was that p is less than 0.5. So we have to look at the less than, which is that middle one. Okay. Everything seems to be correct. Let's go ahead and calculate this. Okay. So our z-score is negative 1.29 if we're rounding. And our p-value is 0.0994 if we round to 4 decimal places. That's complete step 3. And in step 4, I'm going to go ahead and write down what the p-value was first before I close my calculator. 0.0994. Okay, now we're going to draw that bell-shaped curve. 0 is at the center because it's a standard normal. We want to label the test stat that we got in step 3 as a negative 1.29. And we are shading in what direction? Well, in the alternative hypothesis says that p is less than 0.5. So we do have to shade in that direction, less than. Okay, and what's the area of that shaded region? Well, that is the p-value. So everything's labeled. We have the correct graph. We have the 0 labeled, the test stat labeled, the correct direction is shaded, the correct number of tails are given, and the p-value is labeled. So there's a lot of things in that step 4. And then step 5, we have to make a decision. And the decision is made by comparing your p-value to your significance level. What was the significance level in step 2? Just 5%. P-value is 0.0994. So now p-value is greater than the alpha, so we're not going to reject. Fail to reject the null hypothesis. Okay. Why? Because 9% is larger than the 5%. We were willing to be up to 5% chance of being wrong. In this case, if we reject the null hypothesis, there's about a 9.94% chance of being wrong. We weren't willing to take that risk. Okay, so in this case, to come up with a conclusion statement, step 6, the alternative was the claim, and then we failed to reject the null hypothesis. Let's go up to the flowchart up there. Okay, So we follow this. The alternative was a claim, so we're down here. And we failed to reject, so we have to use that bottom one there. So there is not sufficient sample evidence to support the claim that less than half of all voters prefer the Democrat. There is not sufficient sample evidence to support, that's a key word there, the claim that, in this case, less than half of all voters prefer Democrat. That less than half of all voters prefer the Democrat. All right, thanks for watching.